right, looks like most of the people have rolled in. Thank you for coming. I'm here with my coworker Dima to talk about multi-tenant, multi-cluster, and multi-container Apache Hbase deployments. So who are we? I'm Jonathan Shea. I'm the tech lead of the Hbase team at Cloudera. I'm a member of the Apache Hbase PMC and the founder of a project called Apache Flume. Dima Spivak, he's our QE lead for the Hbase project at Cloudera. So let me ask one quick question. How many of you guys are actually using Hbase today? That's great. In production or just testing and just trying it out? Production? Yes. Oh, okay, great. Hbase has come a long way, and it's pretty exciting to see that many people using it. So for those who have not, Hbase is a consistent, low latency, random access, non-relational database built on top of Apache Hadoop. It's modeled after the Google Bigtable paper, and it's basically meant to scale to handle many, many rows and large amounts of data in a tabular format. There are many companies who use, contribute to, or provide services that use Hbase underneath. This is just a sampling that I've gathered from various users that have given talks in the past, meetups and whatnot. So some highlights, there's Cloudera, Intel, Hortonworks. They're large contributors. Large Chinese companies like Xiaomi. There's been contributions by Google and Microsoft these days. Apple's been reported to have used it, as well as many other companies in ad tech, biotech, medical device, medical areas, financial, etc. So lots of different kinds of users using Hbase for all kinds of different kinds of applications. So what really happens after you start using Hbase in production, you get to a point where you have one application that's running really well, and you run into a couple new questions, and that's what this talk is going to hopefully try to address. So, if you have a successful Hbase deployment with one application on it, how do I run with two applications? How do I run with multiple applications? What are the strategies I can use to have multiple workloads on either the same data or different sets of data? How do I share this data between the different workloads effectively? How do I have a disaster recovery plan? Do I use something like Geographic redundancy, having Hbase in two different data centers? How do I do that? And what are the strategies and what are the tools in place for Hbase to help you there? How do I deal with migrations? One very standard way of doing it is to stand up another cluster somewhere else and to transfer data. And how do I test things? How do I test my application on top of Hbase and simulate or try actual failures along the way? And what I claim is that there are multiple solutions. There are multiple multi-solutions. So first I'm going to talk about multi-cluster, and that's having more than one cluster for one giant application. I'm going to talk about multi-tenancy and how we have multiple workloads on one cluster. And then I'm going to hand it over to Dima so he can talk about multi-container deployments, how we run entire Hbase clusters or multiple Hbase clusters on one machine. So start off with multi-cluster. So what we're trying to do here is that we're trying to deploy multiple Hbase clusters serving generally one application or one use case. There's kind of two different motivations for doing this. One of them is to isolate different kinds of workloads from each other. And I'll give you an example of that in the following slides. The other reason is to provide geographic disaster recovery. If I have a European cluster and I have an American cluster, I'd ideally be able to not necessarily back things up, but have copies of the data in both continents in case something happens on one. So goal number one is isolation, right? If we have multiple workloads running on the same cluster, they're going to fight for the same resources on the machines in that cluster. And there's different kinds of styles, but when you're doing a multi-cluster deployment, this is generally because you have two different workloads potentially working on the same data set, or two completely disjoint workloads, two completely disjoint applications. One very common case is where you have a very latency-sensitive application. Let's say something that's serving data in near real time to a web page or to a dashboard or something like that. But you also periodically want to run an analytic job that's going to march through all the data in the tables. So how do you make sure that these analytic jobs don't destroy the latency of your real-time application? The other approach is to have two disjoint applications that are kind of running next to each other. So in deployments that we've seen, we've had customers use their main application in one Hbase cluster and have an Hbase cluster next to it recording data using a system called OpenTSDB, Open Time Series Database, for recording metrics on all these different machines and for the applications. So what does this look like? So a multi-cluster deployment that has been used in the past, and that's actually something we recommend if you have a real-time workload, something that we have recommended if you have a real-time workload and an analytic workload, is to use the replication mechanism in Hbase to copy data from your real-time system to a different cluster that has all the analytic jobs running on it. So when we do this, we have the real-time workloads hitting the primary cluster, and it's able to serve all these requests with low latency because it's isolated from the full scan workload that will really hurt the latencies of these low latency queries. We're using the replication mechanism to efficiently copy data from one cluster to another, and we'll run MapReduce jobs on the analytic cluster, saving us from the trouble of having these large scans affecting the performance. Another reason for doing this is the geographic redundancy and availability and recovery story, right? So what we're doing here is we're running multiple Hbase clusters in multiple data centers. Oftentimes, this is done in a podding scheme. So for some of our largest customers, they actually have on the order of tens of clusters, each of which have about 100 to 150 nodes in each cluster. They actually shard the workloads so that different pods, different clusters of 100 to 150 nodes, are responsible for different partitions of the entire data set. You basically have a setup where you have a primary for a particular set of keys or a particular set of data, and it's using the replication mechanism or some kind of mechanism to copy data to the other one. So you have a backup copy living on a different cluster somewhere else. You have a primary cluster because by doing that, you'll get locality, geographic locality in this particular case. So if I'm hitting a service and I'm in Europe, it makes more sense for me to hit the servers in Europe than it would be to hit the servers in the United States. Whereas if I was in the United States, it would make sense for me to hit the servers in the United States, right? So at the application level, these requests are kind of pointed at their geographically close data center. It can also be used for compliance. Some countries have different privacy laws than others, and you can set up this replication mechanism to guarantee that data either stays in one locality or gets shipped off potentially to other localities. And one final use case is for availability, right? So if a data center actually goes down, your application could have the smarts in it to reroute and get access to the data in a different cluster that has a copy of that data. The way we do this, there's two sets of tools. One that's been in Hbase for a very long time and is fairly robust, which is Hbase replication. And another mechanism that I'll talk about that's relatively new that'll help application builders try to get higher availability in a multi-cluster situation. So the primary mechanism we recommend is using master-master replication. So you basically set up a set of clusters in a loop. So you point the different clusters kind of in a ring. And what ends up happening is we use a log shipping technique to ship logs from one cluster to the next cluster, to the next cluster, to the next cluster. And based on some tagging information we put on these logs, they don't get replicated back to the original cluster. So by setting up a cycle like this, we're able to get all of the data to all of the clusters in the cycle. The other thing I wanted to talk about is a library that we've put up on GitHub for folks to use, and this is a multi-cluster client. It gives you high availability with eventual consistency when you're using the replication mechanism. So what does that really mean? It's actually a pretty simple implementation, and it's very similar to HDFS's hedged reads feature and the new read replica feature that's found in Hbase 1.0 and Hbase 1.1, which will be forthcoming. The idea here is that I'm going to make a request to my local cluster or my primary cluster, and if it's taking too long to get an answer, I will go ask the question to the secondary cluster. And in the event that the connectivity to the primary cluster is not available or it's taking too long, I'll get a stale, potentially, answer from the secondary cluster. The nice thing about the way we've written this library is that it uses exactly the same APIs as you would with a single cluster. So when you create a connection to an Hbase cluster, you use this factory to create a connection or an HConnection object, and you issue a bunch of these APIs out to it. What we've done is we've added a new factory that has configuration information to let you point to one cluster or the other, specifying one as a primary or a secondary. And all of your code basically has to do is do a one-line change in a constructor. And then you'll be using the multi-cluster client. We're calling this Hbase MCC for multi-cluster client. And this will be available packaged in Cloudera Labs in the near future. But if you are interested, there's a link below to a GitHub site where you can test out and try out the code. The graphs that I have here are showing the latencies and the performance of this multi-cluster client. So they are all aligned time-wise. I know it's relatively hard to see from visually, but basically the x-axis is time. On the top graph, that's when we're primarily hitting the primary cluster, the blue cluster. We take the cluster down, and all the requests end up going to the red cluster. And then we bring back up the blue cluster, and the requests now go back to the blue cluster primarily. You can see some of the requests actually are going to the red cluster while both clusters are up, because the blue cluster must have hit some kind of hiccup, had been a little bit slow, and we actually go get our result from the other cluster. And as you can see on the second line, what is the maximum and what are the worst latencies that we hit when we are using this multi-cluster client? It's actually pretty good. There's a couple spikes where it gets up to 12 milliseconds, but in this particular test, it's averaging out to about 5 milliseconds per request, whether it's local or remote. Sorry, that's the averages. The maximum, you can see a couple spikes where you get into the hundreds of milliseconds, but for the most part, it's fairly good and in the low tens of milliseconds for request response times. All right, so that's kind of the multi-cluster story. We have two main mechanisms, replication and the multi-cluster client. Next, I'm going to talk about multi-tenancy and what I mean by that, and I'll define it in the context of Hbase. Multi-tenant workloads. So here's when we deploy multiple workloads or multiple applications on a single cluster. And we'd want to do this to get better resource utilization. Maybe your application isn't using all the resources on that particular cluster. Maybe some cost efficiency or operational efficiency. Only having to administer one system is much easier than having to administer multiple. Simpler operations, shared data. So in the previous situation, it's the same set of data, but we've split things up so that you have a real-time workload and a analytic workload. Ideally, we would be able to do this on a single cluster. What can we do for this? There's also another situation which I'll talk briefly about, which is when you're having multiple services on the same cluster. So having Hbase run with latency guarantees while trying to run a system like Spark, Impala, or MapReduce jobs. One thing that we introduce with multi-tenancy is security problems and security concerns. And one of the major features that we've added in Hbase 96 and extended in 98 and 1.0 is a namespaces feature. Namespaces basically allow you to have multiple administrative domains within one Hbase cluster. And you can have essentially an admin responsible for one set of tables and a different admin responsible for a different set of tables. We use the Kerberos authentication mechanisms, and we've built in the authentication mechanisms, and Hbase has its own internal authorization mechanisms to allow or disallow queries or metadata operations. And we've threaded this throughout the system now so that we can control which rows or which columns a particular user is allowed to see. We've isolated the administrative domains so that we have different admins. And we've also added impersonation features to our proxies so that oftentimes people deploy a thrift proxy in front of Hbase so that they can talk to Hbase, let's say using Python or Ruby or whatever their other favorite languages are. And what we allow you to do is impersonate another user now using Kerberos and using these strong authentication mechanisms in order to have those credentials that you have to, let's say, Hue, which is a nice front end, get propagated through and only allow you to get the data that you're actually allowed to get. So one of the features that we added, it to CDH. It's actually in the upstream Apache. It just got backported to the 1.1 branch, so it should be available in about a month or two in the Apache releases, is a request throttling feature. And this is actually one mechanism that helps try to address the problem of having a real-time workload and an analytic workload on the same Hbase cluster. The idea is pretty simple. Certain users have no throttle, so they can use as much of the resources as they can get their share of. And other users have a throttle. And what this means is they can only get a certain number of requests or a certain amount of throughput per given amount of time. So the ideal way to use this is to say the real-time workload has no throttle. The MapReduce job is being run by this MapRed user or some other user, and we would put a throttle on that particular user. You can see from the graph, the top graph, we show the blue line. That's overall throughput. And it's essentially the same despite whatever throttling values that we show on the x-axis. When we have no throttling on either client or either application, the orange one or the red one, each application gets about a fair share. It's roughly the same. But as we turn on the throttle and as we make the throttle tighter and tighter on the orange application, you can see that the amount of requests that the orange application gets goes down, and the number of requests that the red application actually handles goes up. I should have fixed the colors on this on the graph below, but basically what we're showing below is the latency effect as well. So what we're seeing is the throttled one, the throttled application, latencies are actually going up, which is kind of okay for that particular application. And our real-time unthrottled application remains and actually improves its latency or average latencies on these requests. All right. We've also added another mechanism side of Hbase, and this is a request scheduling mechanism. And the fundamental idea behind this is that a real-time workload generally will do small get operations, and an analytic workload will do long scans. We'll try to march through entire sets of large chunks or the entire table. So the idea here is that these gets, they actually pull out and get one of these scanner IDs. And if it's a new scanner ID, we give it very high priority. We let it kind of jump into the front of the line. Or we have a regular queue and it goes there. But if this is a long scan, this scanner ID gets used over and over and over. So what we do is we keep track of the number of times it's been used and penalize it. We basically delay schedule it, say, hey, you've already used this 5 times, 10 times. We're going to push you further back, and we're going to let these other guys that are newer preempt your requests. So what you can see here from the illustration is that this is the top one is kind of the natural order. Let's say that's the order that the request came into the particular server. But with this scheduling mechanism, we've rescheduled the blue one that has multiple parts and multiple uses of that scanner ID in order to let the real-time application and the real-time requests happen more quickly than the requests that have been pushed back because they're longer scans. The one caveat with this one is that it requires some tuning for your application. One other mechanism that is kind of in the proposal phase, there are patches up and we're in the process of reviewing. It's actually been around for a long time, and it's actually one that's been used in Yahoo's Hbase clusters in production for quite a while, is an idea called a region server group. So this isn't in any version of Hbase that you can download today, but it's been used in Yahoo for quite a while. The idea here is that we might have multiple tables with multiple workloads. Let's say a light blue, a dark blue, and a gray workload, different applications. And they've spread their partitions out across the cluster. What we do is we say certain machines belong to a particular region server group, and we isolate, let's say in this particular case, the dark blue application to one region server group, and then the light blue and the gray go to the other region server group. So what we're really doing is we're isolating the physical resources within a single cluster. And generally this is done by namespace. That was that abstraction that was brought in a year and a half ago or so. The goal here, obviously, or maybe not obviously, the goal here is to host several applications, more than 1, 2, 3, whatever, to host multiple applications in one cluster. All right. So I mentioned I have one slide on service isolation. So unfortunately, the best thing that we recommend today is to statically partition your different services. So if you're running Hbase and latency is very critical to you, instead of having the situation on the left where we have all the services deployed on all the machines, what we actually do is we recommend splitting up the different services so that Hbase is not impacted, or these other applications, these other services are not affected by I/O between the different systems. So in particular, a system like Impala will go to the local file system to spill, and so will MapReduce. And that's kind of outside of the bounds of what Yarn could even control necessarily. So by separating these kinds of things, we are essentially isolating I/O, which is the most important thing in Hbase's point of view. Now, in the future, there are probably improvements that are on their way. There have been talks about Slider and using Yarn as a resource manager. At the moment, the I/O is not managed by Yarn, so that would have to be an extension put into that particular system. There's another system called Mesos, and I personally haven't tried it, but that's another potential angle to address this multi-service problem. Another thing that we are considering is breaking up some of the Hbase pieces so that I/O-heavy routines get pushed out to separate processes. This is kind of a twinkle in our eye right now, but it's one potential way to address the compaction problem or the write amplification problem that we have occasionally in Hbase. All right, that's it for multi-tenancy. That's it for multi-cluster. I'm going to hand it over to Dima, and he'll talk about multi-container.
Hello. So multi-container is an interesting topic because what John just described were basically what you could sort of think of as almost kind of canonical deployments of Hbase. You have a bank of machines, you want to run something in production, but I'm not a developer of Hbase. I'm a test engineer. I work on the test team at Cloudera. And we run into a very different problem, which is that as all these new features come into Hbase, you want to do two things. One is, first of all, you obviously want to verify correctness of the feature itself, right? So you introduce some new feature that's supposed to improve performance. You want to make sure that you can turn on that feature and that scans still work the right way, that you don't start getting correctness problems when you turn that on. But the other thing that starts happening is that you then wonder, well, all these new features are in the write path or the read paths, these really kind of critical places of Hbase. What happens if at the moment that one of these clients is doing something, a region server goes down or the master goes down, and you want to make sure to test this kind of fault injection case? So what ended up happening with us at Cloudera was that, at first we began by having, just 4 or 5 node clusters, and we would have to sort of figure out scheduling across, all these features that are coming in. And the number of permutations you get of these configurations is really, it's kind of mind-boggling. You guys know combinatorics. It gets pretty bad pretty fast. So we started looking for a solution over a year ago to basically see if we could both better take advantage of resources and also not only physical resources, but also kind of human resources. Because anyone who's stood up a full kind of Hadoop cluster knows that it's not a trivial operation, and in some cases it's not, it's not a 3-minute operation for the most part, right? So the way we addressed this was with what we're calling multi-container deployments. So in particular, what this means at the moment for us is running a distributed Hbase cluster on a single host, all right? The normal use case for this that people who do work on Hbase clusters in production for is to test applications. So if you have something that's based on Hbase and before you kind of push it into production, you want to tweak your configuration settings, tweak whether things are falling over the right way. you want to have some way of quickly standing up a cluster. And that's really the important point here, is having the ability to really quickly stand up an Hbase cluster. And in our case, on the test team, at least at Cloudera, it's not just Hbase we cared about, it was actually the whole stack. But for this talk, we're really going to focus on Hbase. So when you hear multi-container, or I guess in general, when you hear container, what are containers? So at a very kind of naive, high level, you can start with Linux containers, all right? So this is something that's been in the Linux kernel since 2.6, 20, or 24, or something like that. And it's based on basically resource isolation. So this theme we're kind of coming back to a few times now in this talk is isolation of resources. And the way Linux containers does this is with something called C groups or control groups. And control groups basically have a relatively fine-grained way of letting you isolate resources within an operating system. So this could be things like memory. So this could say, limit this container to only be allowed X amount of RAM. It could also be things like block I/O. It could be network isolation. It could be CPU cycles, things like that. So you have isolation of resources. But the other thing that's very important is isolation of your namespace and file system isolation. You want to be able to say, on a single operating system, I want to have two environments that are running that are not aware of each other and that won't mess each other up, okay, if they're both running at the same time. And when you talk about Linux containers nowadays, in this kind of way, when you're talking about isolation of resources on a host, the natural question is, all right, well, how does this compare to virtual machines? So I've reproduced the diagram that you'll see in 300 talks this year, which is to say that, virtual machines at a very high level are a host operating system and then a hypervisor that basically acts as this conduit between your virtual machine environment and your host operating system. And so if you want to start up, for example, 4 VMs on a host operating system, you'll have this hypervisor running, you'll stand up a guest operating system, and then within that you'll have your libraries, and then finally your user processes on top of that. And this works really well. You look at all kinds of hosted solutions that run on VMs. This is kind of a tried and tested way to isolate resources on one machine. But what you notice is that if you want to stand up like 4 of these, if I want to run a cluster, you do notice that there's kind of this overhead involved, right? Where you're basically reproducing a guest operating system. You're reproducing these libraries that in theory could have been shared across all your virtual machines in the normal kind of standard way of doing this. So containers could do this in a slightly different way, because with a container, you still have your host operating system, but you don't have a hypervisor. And the reason is because it's the host operating system's kernel that actually acts as the kernel of this container, the containerized environment. So that is to say that you don't have to have this conduit between a guest operating system and your host, all right? And in fact, along with that, even things like libraries, if you're standing up things in a certain way, even the libraries could be shared across these instances of containers. And then from there, you still can have good isolation of your user processes. You still have unique process trees across your containers. But even from this kind of silly diagram, you see that you're taking out the need for resources to run things that you might not necessarily need for your environment. So you're talking about Linux containers. Even at this conference, you're aware of the fact that Docker is kind of the place to be when it comes to Linux containers. And even though they now use libcontainer, it's still this idea. So for anyone who hasn't heard of Docker, welcome. But basically, at a really kind of, again, naive level, you could think of Docker as a user front end for containers, okay? And for our purposes, we really take advantage of this user front end with basically the 3 commands we use most. So first of all, you want Docker because it gives you container management, which is to say it gives a really simple API to start containers, to stop containers, to pause them if you want to pause the container environment, and that's using this so-called Docker run command. So if you ever play with Docker, this will be the main command you ever use. The second feature of Docker that's really helpful, especially for our testing purposes, because once we set up an environment, we don't want to have to every single time set it up again from scratch, is the notion of images in Docker. So you could think of images as kind of like a static template from which you can start with a container, and then you can sort of preserve it and almost, serialize it into this image format, kind of like just like a zipped up thing, by using a command called docker commit. So I could start up a container with docker run. I could do things in that containerized environment, which thinks, for all intents and purposes, that it's on its own kind of machine, and then I can commit that container into an image. And then later on, I could pass that image to a friend and have them start up the same environment. And then lastly, the third feature of Docker that we use very heavily at Cloudera is the notion of the Docker registry. Docker registries are basically like repositories, and the nomenclature gets really weird with Docker because they pick funny names for things. But it's basically just a repository for images. So if you're in a team and you guys are each developing images of things that are useful for your application, you could do Docker push to create that, to take that image, push it into a shared Docker registry, whether a private one or the one on Docker Hub. And then anyone else in the team can pull down that image without having to build it from scratch. Okay. So this is the 3-second introduction to what Docker is. And I'm going to describe sort of how we ended up using this for something useful internally at Cloudera and shortly up in the Apache community as well. And that's integration testing. So one of the things which we're kind of blessed with Hbase is that for a long time on Hbase, there's been a great interest in actually having integration testing. So you don't want to just do unit testing of features in Hbase. You actually want to stand up a cluster, or if you already have a cluster, use that cluster and do some long-running tests along with things like fault injection. Okay, so a very common one is something called integration test big linked list, which basically lets you write a lot of data into Hbase, and then you can scan through it again and make sure that you're not missing any data. And meanwhile, you're trying to kill region servers or masters, or you're triggering compactions. You're basically trying to see that if a user is actually using Hbase in a way we want them to, that it works like a database should. So how do we do integration testing with what I've just described, and how does this relate to Docker? So what we basically do is, as I said, we want to start with a single host and stand up a full distributed Hbase cluster on that host. And the way we do it is by basically running a simple, we have a command called start cluster. And anybody that uses Docker knows that one of the main shortcomings of Docker that's being worked on a lot in the upstream community is orchestration of containers across hosts, okay? Which is to say that Docker containers, by default, are not very good at talking to each other in a really simple way. And for the most part, like people who normally use Docker don't try to use containers as if they're machines. And in our case, we're trying to do exactly that. We're trying to test a distributed Hbase environment using Docker containers. So when we start a container cluster, at a high level, here's what we do. We begin by actually starting a DNS server. All right, so we start a DNS server because we want to have a central kind of source of truth for IP addresses and host names for this container cluster that we have. And again, because Docker containers are really lightweight, we tend to start the DNS server in another Docker container. Then for our purposes, what we do is we start up the first node of that cluster. And this tends to be a pre-made image that I call it here like a master image. And the reason it's a master image is because if you want to set up a 4-node cluster of Hadoop, what you tend to see is people tend to put like the name node and maybe the hmaster on one node, and then the remaining nodes tend to be your data node and your region servers. And this is kind of this, in the simplest case, this is one way to do it. And that's exactly what we do. So we have these pre-created images that have this master profile that has, again, your name node and your hmaster. We start that up. And then we start up a second node, which would have, again, the data node, the region server. And in our case, because we're using, we're from Cloudera, we use Cloudera Manager for the orchestration of our roles. You can actually take this second image, this slave image, and actually start it up multiple times. And by talking to the DNS server in the right way, what ends up happening when you're done with this is that, for all intents and purposes, you have a 4-node cluster running on this host. Each node has its own IP address. And if you SSH into node 1 and start typing things into an Hbase shell, it has no idea that it's actually running on one physical machine. So we took away the need to have 4 machines at a time. On one machine, we can actually do this. And the reason we want to do this is for automation purposes. So as I said, one of the things that Hbase has upstream is this notion of integration testing. But the integration testing Hbase has was never the one piece of it that was always missing, basically, was standing up a cluster for basically upstream testing purposes. At the moment, there's no place upstream where you can run these integration tests and see day to day whether one of these long-running tests has started failing or not. And that's something that we wanted to fix internally at Cloudera before pushing upstream. So what I'm showing here is a simple Jenkins job called Docker Hbase IT. And on the x-axis, you see a suite of 5 integration tests. These are all from upstream Apache Hbase. You can run any of these on your cluster by just going in and typing Hbase and then putting in the full class path of the integration test. And then on the y-axis, you actually have what are called chaos monkey profiles, or actions, or policies. And what these specify is basically, while running the test on the x-axis, do something on that cluster to either kill region servers or trigger compactions. You could stress your assignment manager, basically things that a customer might see happen in their use case. You actually want to trigger those kind of worst case scenarios while running these tests and see if the tests start failing or not. And we started doing this internally at Cloudera so that every night, whenever we do a full build of CDH, that we actually do set off this full suite of tests. And one of the nice things with the Jenkins automation with this is that you can actually, because you only need one machine for this full cluster, in this case we have a 5x6 grid, we have 30 machines. You can actually dynamically spin up 30 machines or 15 or 10, however many you want to throttle, and then run the full suite of integration tests with all this fault injection really easily through Jenkins. So this is what we've done internally at Cloudera, but now that we kind of got it working internally, we said this is pretty cool. People should take advantage of this. So in progress right now, there's a Jira there. We're actually going to extend this workflow to upstream Apache Hbase so that if somebody wants to download Apache Hbase and stand up a 4-node cluster on their Linux machine, they would be able to type in one command. And then instead of needing to download Hadoop, set up Hadoop, Zookeeper, all that, in about 3 minutes, you'd actually have a distributed Hbase cluster running on a single host. So we're really excited about it. Progress will be coming very quickly, very shortly. And the main goal of this, as I said, is upstream integration testing. The ability to, as new features come in, not just to run unit tests, but actually to have these long-running integration tests that already exist, but just that don't have an automated home upstream. That's the big goal here. So some conclusions about the multi. We've sort of presented all these use cases, these three multis, as kind of separate things, but they're really not. In a lot of ways, you could see sort of themes that cut across both, the multi-cluster, the multi-tenant, and the multi-container deployment types. So the common themes are things like isolation of workloads. I'm not just going to read off straight off the grid, but basically all three of these paradigms have ways that deal with isolation of workloads. And at the same time, while they have ways of dealing with isolation, they also do work on things like having multiple workloads on one set of data. You don't want to necessarily be moving a lot of data back and forth if you're going to just do different operations on the same set of data. You deal with things like reliability and availability. This cuts across everything because obviously if you're working on a distributed system, one of the reasons is because for your use case, reliability and availability is probably something you care about. And lastly, cost savings. This is a really big one, especially on the testing side for me, because again, if you can reduce the number of machines you need by a factor of 5 and still get the same testing done, that's always a nice thing. But things like disaster recovery, all kind of renowned for being money sinks when things go bad. So that's a summary. Some final futures here is that in general, we're seeing more and more deployments that are multi-cluster and multi-tenant. And in particular, you're seeing that these sort of traditional deployments where you're devoting a full cluster just to HBase, they're really giving way to hybrid kind of scenarios where people want to run Spark, they want to run MapReduce queries on the same machines as they're running an HBase instance. And in particular, you have to just keep in mind here that now you have more knobs to turn. So in other words, you no longer have to think about just being a service on its own on your cluster. You have to now think of how are your settings going to impact the other services that you're running. And then lastly, these multi-container deployments, it's something newer. It's not something that's just a traditional thing that you can add now. But we think it's a really useful way forward, especially for prototyping and testing HBase and making deployments easier. So thank you. And before we finish, we also just want to quickly plug that if you are interested in HBase, which it seems like people in this room at least seem to be, HBaseCon 2015 is coming up next month. So if you're in San Francisco, please register. It will be good. Thank you. Right.
Time for a couple questions.
I have a question about the multi-cluster client. Isn't there a risk of a snowball effect of your first cluster being not responsive enough, so all queries are routed to the second one and so on? And do you have mitigation parameters or thing to prevent that?
So the idea is that one of the primary places you might use this multi-cluster client is in a maintenance window kind of situation where you have one cluster that is being upgraded or something that you're concerned about. So you could kind of shut off the traffic to that, and you kind of expect and hope that the data would go to the other cluster while this event is happening. We don't have any mediation or throttling to prevent a large amount of that data going there. That's not one of the original concerns, I guess, with this project. But as people use it more, that probably is something we would be more concerned with. Any other questions?
Up front.
About the Docker container, how do you handle the IP DNS registration?
So we just use DNS mask. So we just run DNS mask in the container, and then when we add nodes to a cluster, we just write a host name and IP address into that container. Yep. Any others? Oh.
Just a short question. Is that somewhere available? The Docker project you talked about?
Yeah, so the Jira that we listed at the end here is going to track this, what we're calling Hbase Docker. So yeah, it will be available very shortly upstream. Okay.
Well, if there are any other questions, we'll be up here, or we'll go over there, and you can ask away.
Thank you.
Thank you.